Welcome everyone. I'm really happy you're able to join us for this webinar. This is one of our academic series webinars, and this is a little bit of a special one because most of our webinars are about JMP, so the general product that we have. This webinar we wanted to do specifically for advanced researchers, so JMP Pro, which is really the advanced version of our JMP software. And so before I tell you about JMP Pro, before I get into any of that, let me just give you a little bit of an idea of what today will look like, and also a little bit of an idea of who I am, so you can put in context a number of the things that I'll be telling you about JMP Pro. Now first, what are we going to do today? And my schedule here is I want to introduce you to what JMP Pro is generally first. We're actually looking at the web page on the right, and I'll take you through that too. We're going to dissect or go through really the special Pro features, the Pro-only features that are really useful for academic or regular research. And what I'm going to do with each of these is wrap them around case studies. Of course, tools are useful for a lot of different things, and I think it's more interesting and useful to know the situations that tools are valuable for. And so we're going to step through those. I'll make sure to leave you with some links so you can always learn more. And by the end of the day, hopefully you'll see the reason why we think JMP Pro is so great for advanced research. Now, a little bit of a background about me. I've been using JMP for about a decade. I started in grad school, and actually my background, I'm not a statistician, I'm a researcher. So my background is experimental psychology and cognitive science. And so I'm most interested in getting meaning from data. I mean, I love getting new research data. I'm sure most of you do too. And my favorite part is uncovering those mysteries that are in the data and seeing what's in there. And having tools like what's in JMP Pro give you different and new ways to really see and get insights from your data. And I just love that. I think learning a new tool is a wonderful thing to do because the more tools you know, the more creative ideas you have about research. You know, once you know how to swing a hammer, you start to think about all the houses you can build. And so I think JMP Pro opens up a lot of doors for researchers, and that's sort of how I come to it. Okay, so on the right-hand side, I'm showing you actually the JMP.com Pro page. And this will take you through, if you want to look at it, a lot of the big sort of overviews of what JMP Pro can do. And so the key features are all listed here. Many of these we're going to talk about on the left-hand side, but you can see there's a lot of detail here. There's a lot that JMP Pro is. And so I want to sort of break this down in the simplest possible way. What is JMP Pro? And this is going to be my variant of that page. JMP Pro is the most advanced graphical interface to data ever created. And I realize that's a little bit hyperbolic, but I have used every statistical software under the sun. And there is nothing, at least for me, that compares to the power, the ease of use, and the speed of JMP Pro. It literally changed my research career because I could do more quicker. So let's actually step right into JMP Pro, and let's sort of see what I mean about it being this powerful way to understand data. And we're actually in JMP already. This is just a little journal for JMP. But what I'm going to do is pull open some data, and we're going to step through some of these Pro features, and I want to make sure you see why they're useful. Okay, so the first one, I'm going to pull open a data set called fitness. And before we even talk about the topic of bootstrapping, let me just very quickly orient you to JMP if you've never seen JMP at all. So I assume many of you are here to learn about JMP Pro, but maybe some of you have never even seen JMP. So JMP is desktop statistical software, runs on the Mac and the PC. I happen to be running on the Mac here, but it looks the same on Windows. JMP is graphical, menu-driven. So if we go to any of our menus, you can basically create analyses and output without ever having to write code. Of course, you can code if you want. There's a full programming language in JMP. It's called JSL. But the value of JMP is to be very quick and to be able to look through your data by just pointing and clicking. So I produce some output here. And the beauty of JMP is that everything works like a modern piece of software would. You can click on things and they're active. These are not just static windows, right? These are interactive outputs that allow you to dig through and see things in your data. And also a characteristic feature of JMP is that it's very graphics forward. You always get a graph first. And when you produce new output, for instance, I'll just turn on a normal quantile plot, those outputs populate the same window. And so it's not like a log window that you might be used to in older software where you produce output and then it gets shoved to a log. These are little interfaces to data, and they're active interfaces. I can select things, and they're selected everywhere. And so when I say that JMP is the most advanced graphical interface to data, I mean interface in a very pointed, specific way. It is not just data analysis. This allows you to interface with data. So that's a really brief introduction to just JMP. Now, what is it about JMP Pro that sets it apart? Okay, so the first thing I want to talk about is the idea of bootstrapping. And the why here is really when you want to perform analyses and you have some parameter of interest, let's say it's the mean, you often want to put confidence intervals around those parameters. You take a sample and you know that your sample mean may not be exactly equal to the population. So for instance, I have data here in fitness for 31 individuals. Let's say we were really interested in the running pulse of all these individuals. And so let me pull open a platform I just showed you, that distribution platform. And I'm going to tell JMP that I just want to look at the univariate characteristics of running pulse. All right, so here we have a mean, 169. But as I said, and as I think we all know, sample means aren't the same as population parameters. And so what we are trying to do is put intervals or confidence intervals around these. Now with parametric assumptions, if we assume certain things about the population, then the upper and lower confidence intervals that are reported automatically are perfectly fine. But let's imagine that we can't make the parametric assumptions. We don't think the population is normal, or we don't even know anything about the population. How can we form an estimate and an interval around an estimate without knowing this? So this is what bootstrapping is. Bootstrapping is a technique where we continuously and iteratively take samples or subsamples of this data set and calculate the statistic we want. And what we form is a distribution of that statistic over the repeated samples from the same data table. Let me just show you what this looks like, and we'll actually get a better sense of what it does. Now, to clean things up just for a second, I'm going to click this red triangle. In JMP, red triangles are little menus, so if you're just learning JMP, always click those. And I'm going to customize the summary statistics because I want to turn on one that's actually really hard to get a confidence interval for. I want to turn on the skewness. So skewness is how non-symmetric a distribution is. And skewness, negative 0.34, so it's a little bit left skewed or negatively skewed, we don't have a confidence interval for that. That's something we don't have a sampling distribution known for, so we don't have a parametric confidence interval. Now, if we wanted to make one, here's how you do it in JMP. This is the how. And in JMP, it's called one-click bootstrapping. You just right-click a table and select bootstrap. So let's do it. I'm going to right-click this table. I'm going to select bootstrap. And what JMP is going to ask me is how many times do I want to subsample from this table? Do I want to do 100 subsamples? Do I want to do 1,000? Let's do 1,000. And I recommend when you're doing bootstrapping for actual research, you do the minimum of 1,000. Now what this is going to do is very quickly, it's going to subsample from my table, give fractional weights. I checked that box. And it's performing this bootstrapping procedure as a way to figure out how reliable is this skewness figure. Is it depending on just a few people? Because when I take subsamples, I don't always get the same people. So what I'm going to get at the end of this is a brand new table, 1,001 rows long, because my original sample is there, and the 1,000 bootstrap samples. And for each one, JMP calculated that skewness. So for every one, it's like it ran a distribution report and entered the value to a table. Now the power of this is, let's go back to the Analyze menu and use distribution again, because what I want to look at is over those 1,000 samples, what types of skewness measures did I get? That'll give me an idea of what potentially is true in the population. And notice what JMP does. JMP knows that this was a bootstrapped table, and so it's given me the confidence limits. And basically I can look at the confidence interval and say, well, it includes 0, and a rule for confidence intervals is if it overlaps 0, then 0 is a possible candidate for that parameter in the population. So basically what we're saying here is, yeah, in the population, we actually don't really have great evidence that there's skew out there. It's potentially a possibility that 0 for skewness is the true population parameter. Now, this opens up a lot of doors. This is what I mean about learning a tool, or like learning a hammer, and now you know all these things you can build. Think about all the different statistics you may want to use for inference that you just don't have a test for. So we used skewness here. That's one that typically there isn't a test for, but it could be any of these. You could bootstrap the mode, the median. Oftentimes we would love a confidence interval around a median if we're reporting it. And often if you're reporting things like financial figures, the median makes the most sense. So bootstrap it. Bootstrap that statistic. And this works all over JMP. So for instance, let's say you're fitting a linear regression. I'll do this quickly. It's under fit y by x. That's the bivariate platform. And so if you're fitting a regression, let's say looking at running pulse as a function of weight, I'll just put them both in. JMP is smart. It knows that when you have two continuous variables, two numeric variables, to offer you things like lines or polynomials or non-parametric densities, I'll fit a line. And what I'm doing here is essentially building out a model where I'm interested in, let's say, that slope, the slope for weight of an individual. Are people who are heavier on average having higher or lower running pulses? Well, I have a test of this, And if I want to trust the sort of assumptions of a linear test, so normally distributed residuals, constant variance, all of that, then this is a perfectly fine p-value. But let's try bootstrapping. I'm going to right-click, go to Bootstrap. Just to be quicker, I'll do 100 this time. Again, I usually suggest for research to use at least 1,000. But look what I get is a table now of bootstrap samples for the intercept, that was one of the terms there, and for the weight, the slope. So let's actually look at the distribution over those samples for weight. The idea here being, do we think that that is a stable estimate? In the population, do we think there's a slope? And looking at the bootstrap confidence limits again, we get an idea. Well, our 95% interval does cover 0, so 0 slope in the population is a nice candidate for that. So in essence, not rejecting the null in the same way we did here. So think about bootstrapping as a way to open up the door to any type of analysis you want, any type of inference you like, even if there isn't a proper test for it, because bootstrapping allows you to do that. All right, so that's just one of these, bootstrapping. And one-click bootstrapping is only in Pro. Now, validation is another sort of huge topic area that applies all over JMP. And let me start with just the why. And what I mean here is out-of-sample cross-validation. And validation is a really trusted method that we've always trusted. It's just now that we're couching in a statistical term. And what I mean by this is, in all of science, the hallmark of good science is replication. If you do a study and you find an effect, and then you get a new sample and you find the effect again, replication is a great way to protect yourself from false alarms. Now, validation, or out-of-sample cross-validation, is a way to do that statistically. Now, it's expensive statistically. It means that you're going to hold out part of your data until the very end when you want to test your model. So you're going to use some of your data to fit a model or to predict something, and then you'll use the holdout data to test. And the reason that's valuable is especially once we get down to data mining, these techniques that are built to be opportunistic or to be greedy. Once we get down there, validation will protect us from overfitting a model. Now, we could always do validation. This is always something you can manually do yourself. But the great thing about JMP Pro is validation now is built into platforms. And to sort of give you both an example of how it works, but also a justification for why you need it, I'm going to actually make a new data table. And I want to just do a little simulation for you for why you need to be validating your models. Okay, so to do this, I'm going to do it kind of quickly, but this is just some stuff in JMP to get us a little simulator. So I'm going to go to Add Multiple Columns, and I'm going to add 100 columns to this data set. And what I want is the initial values to be random from a normal distribution, so between 0 and 1, so unit normal. So now we have 100 columns of random data. There is no structure in the quote-unquote population here. These are all randomly varying around 0. And so correlations among any of these, there really shouldn't be any. I mean, there will be some due to randomness, but there's nothing true about a relationship between them. Okay, so let me go to a platform that you may be familiar with, FitModel. FitModel is the more general linear and nonlinear modeling platform. And I'm going to pretend that column 1 was my y, and that the rest of these were all predictors. Now, all of us here playing this game know that there is nothing predictable in column 1 from these in reality. But there will be some correlation, some predictability by chance. What I want to do is go into a platform that you may have used before called Stepwise. And I assume many of you are familiar with stepwise regression. This is a method for picking among these predictors which ones predict column 1 the best. Okay, so I'm going to pretend that we're not using validation. We don't know what that is yet. And we're just going to run this model. And what I'm going to do is I'm going to let JMP try to do the forward stepwise. And I'm just going to hit go. And what it's doing is minimizing what's called the Bayesian information criteria. It's picking these predictors such that it's trying to not overly use too many of them, but it's trying to find ones that are actually predictive of our y. Now, it found 8. It found 8 that actually exceeded the threshold to be included in the model. Now, of course, we know among those 100, actually none of those in reality predict y, but some of them will exceed the criterion for predicting better than chance would expect. Of course, we always accept false alarms. False alarms is a necessity if we're being lazy by sampling. If we don't want false alarms, we have to measure the whole population. Okay, so this is something we all might do. We collect a lot of different variables. We go into stepwise and we try to predict something. And some of them come up as predictive, 8 in this case. Now, we knew from the start that none of those really were predictive, but the model couldn't know that. Now, what happens if we invoke validation? What happens if we allow JMP to keep some of those data separate and test after it's done the stepwise, test it on the holdout set. Will that protect us from this happening? Well, let's see what happens. So I don't have a validation column yet. I can just click this and JMP will tell me, JMP Pro will say, do you want to create a validation column? I do. So let me click yes. Now the way it works is we're going to specify some proportion of our data that counts as quote unquote training, and another proportion that counts as validation. We can also have a test holdout. So if you are really working with a single huge data set and you really want to make sure your inferences are right, you have 3 steps here: training, validation, and test. Let's just do training and validation for now. So I'm just going to click OK. JMP already entered that in for us. Notice that it's actually a part of our data set now. And so it added a column for us that literally randomly selected rows to be training and validation. Okay, so the only thing that changed between what I'm doing on the left-hand side and what I'm going to be doing here on the right is that the right-hand side stepwise has access to data at the very end to test the model, to make sure it's actually working. So when I click go, hopefully we will have fewer than 8 of these predictors. So only 1 of them now pass muster. So 1 out of 100. Now, this is interesting because before, in fact, no, it wasn't even 1 parameter. It just chose the intercept. So it knew that none of those predictors actually had anything to do with y. So with validation, holding out that 30% of my sample, I mean, it was costly. I had to give up 30 of my subjects to validate the model, but it protected me from spurious findings, from these 8, I guess in this case it was 7, predictors that exceeded the threshold. Now, what's amazing about JMP Pro is that in so many places is validation now just built in. So you saw it in Fit Model. You're going to see it again when I go into some data mining platforms. So for instance, Partition will have a validation section. And these validation options allow JMP to, in an automatic way, create models, and create models in a way that will generalize better. And again, this is a very old idea, the idea of replication. If you can replicate a finding with data that wasn't used to develop the finding, then that's a great way to tell that your model is really working. And this is the age-old problem. You can't use the same data to generate a hypothesis as you use to test a hypothesis. So this is a statistical formalization of what is truly an epistemic issue of how we measure the world. And so validation we'll see a lot today. And I just wanted to give you this little demo to see why it's valuable here. All right, so those two, bootstrapping and validation, really apply all over JMP. And so we're going to keep using them today. Now what I want to get into are some specialty, what we call platforms in JMP, that enable some really sophisticated type research. And perhaps the most important that I want to talk about is the new mixed model platform. Now, mixed models, many of you probably know about or may know by different names: hierarchical linear modeling, multi-level modeling, models with random coefficients or random slopes. So the why here, there's actually several whys, because mixed models are, it's a very large group of different types of modeling. But these are certain types of scenarios where they might be useful. So split plot designs, randomized block designs, panel data models, so in econometrics, any kind of repeated measures where you have within subject errors that are correlated, or hierarchical models, so students within schools, within districts. And also geospatial regression, so when you have spatial variability that you need to take into account. And really all of these whys are at root one issue. The issue is that data points are correlated. And when data points are correlated, are non-independent, this introduces problems for typical general linear model. Basically, in the general linear model, we assume errors, what our model doesn't predict, are uncorrelated across individual units. But with mixed models, imagine a repeated measure situation, the same person participating in the study over and over. Well, that person will have measurements that are correlated from time to time, and more so than the correlations between any random 2 people. So we need our model to acknowledge that and to honor that in our design. All right, so how are we going to do this? Well, it's going to be under the Fit Model platform that I just showed you. But let's actually bring up some data, and I'm going to start with a simple example. And before we even do the modeling, let me just orient you to the data set. These are some data looking at basically different types of wheat and their yields in different types of moisture. And just so you can see what data we're dealing with, let me go to Graph Builder. This is under the Graph menu. Graph Builder is an amazing drag and drop graphing platform. This is a part of regular JMP as well. But what I'm going to do is I'm just going to grab yield and moisture, drop them in the center. So this is the overall trajectory between moisture and yield. So if we just look at this smoother, I'll actually put on a line. As we have moister soil, we tend to have more yield. But the question is that the same for the different varieties? We measured these different varieties multiple times and under different conditions. And so what we're really asking, let me just drag variety into the group for X. And what I'm doing is really saying, for each variety, do we think A, they start off at the same point, that is, they have the same yield on average, so where the middle of these are, and the second question is, do they have the same slope? Is the relationship between yield and moisture the same for each of these? Now, in this case, we can kind of see that it looks like they're pretty similar. That is, the slope between moisture and yield is the same. But what doesn't look to be the same is the center. So the intercept for each of these looks to be different. But we need to acknowledge both those in the model. We need to take that into account and look for it. So how are we going to do this? So again, the way to invoke a mixed model in JMP is going to the Analyze menu, go to Fit Model, and you'll see under Personality. Personality is really what type of modeling scenario do you find yourself in? And there's lots of them in JMP Pro, and several that we're going to see today. But Mixed Model is a special section here. So let's invoke that personality. And what you'll see is you have sections for fixed effects, random effects, and the repeated structure. Now, it's well beyond the scope of today's webinar to teach mixed models, but very briefly, fixed effects are really the factors in your experiment, the thing that you changed. Random effects is really what do you think is noise in the data? What structure is there to the errors? And we'll sort of piece that apart in just a second. And then repeated structure is a section where we can actually define how the variances among people, or how the correlations, let's say, the non-independence, what's the structure of that non-independence? Is it completely random, unstructured, or is there something predictable? And we'll look at a couple of these. And the spatial models make a very obvious prediction. Things that are closer together in space should tend to be more dependent on each other than things that are further apart in space. And so we'll come back to all of this, but let's see how we'll set up this basic model. So what we're predicting is our yield. So that'll go into our Y. What we're having as a fixed effect is the moisture. Now, you might think, why isn't variety a fixed effect? Variety is actually our subjects. That's sort of a random noise that we want to have in here. And what we're really interested in is how moisture affects yield. And these varieties are ways of measuring the effect of moisture. And the way we're going to designate variety here is we need to have an intercept. Remember, those varieties may not start at the same place. And we need separate slopes for each of the varieties. Remember that each one may not have the same relationship between yield and moisture. So here's how it's going to work. We're going to put in moisture first. And then with it selected, I'm going to click Variety and select Nest Random Coefficients. And what this does is it creates two special random effect terms, an intercept for each of the varieties and a slope for each of the varieties. Now I'm going to click Run, and you're going to get a lot of output here in a second. We're going to go through all of it, so hold on a second. But before we do any of that, before we look at any of the statistics, I'm going to turn on something under the red triangle that helps us get the most out of this. It's under the Conditional Model Inference, and I'm going to turn on the Conditional Profiler. Because what this does for me is it turns on this cool little model profiler where we can drag things around to see predictions for yield. But what we get is for each variety, the ability to click through. And if you focus your eyes on the left here, as I click through different varieties, notice that that line is moving up and down. That's the different intercepts for the different varieties. And the slope is changing ever so slightly. Not very much. Remember, we didn't see much change when we used Graph Builder. But that's what this modeling profiler is letting us see. That's what the model we built allowed the data to do. Now, going back to the rest of this, let's work backwards. The fixed effect test is usually the thing most people are interested in. What is our fixed factor or the main factor of interest? Did that have some relationship? And it does here. But we get some extra pieces because of being a mixed model, like the random coefficients. Now, these are, for each of the varieties, the intercepts and the slopes for moisture. And notice that they're actually pretty similar. I mean, we have a lot of decimal places here, but if we had fewer, they would look a lot more similar. And so we actually can diagnose in our model whether we need those random effects. Now, there's some debate statistically as to how you want to go about this. Do you want to remove effects or do you want to keep them in, even if they're shown to be potentially not valuable? And that always depends. And it's really a question on statistical expense. If you have a lot of data, it really doesn't matter if you keep a lot of extra terms in the model. You're not hurting yourself as much. But when you have very small amounts of data, each of these terms costs you degrees of freedom. It costs you little bits of your data in order to make the estimate. And so sometimes parsimonious models are much better at prediction, even though you're missing terms. All right, so notice that the mixed platform here was the only way to really properly do this analysis. With repeated measurements with these individuals or these varieties that we've measured multiple times, we needed to account for that variability. Now let me give you another example, a slightly different example, where we certainly need to account for variability. And this is going to be another repeated measure situation, but one that's a little more complicated. And so in this case, let me just orient you to the data set. We have in this, I'll just drag up my rows here, and columns, there we go. So 120 rows, but what we have is for each patient 6 measurements, because what we've done is we've measured their cholesterol under different treatments at different times. So April, May, and June, both in the morning and in the evening. So once in April, AM and PM, once in May, and once in June. And these other columns here sort of say the same thing. We have days since they started treatment. We had just the time. We have whether it's AM, PM, we have the month, and we have what treatment they're on. So officially, we would say this is a between-subject experiment with different treatments with repeated measurements. So we've measured the people multiple times, but each person is under a different treatment. Now, before we try to model this, let's go back to Graph Builder. And this is one of my favorite ways to just orient myself to the data. Again, use the fact that JMP's an interface to explore. And so let's just build ourselves a little graphic here first. So here's the Y. That's where we're trying to predict cholesterol. I'll just take time here and stick it as my X. So April, May, and then June. We can turn on a line. This is for the overall. But let me actually take treatment and break it apart. So for the treatments A and B and the control and placebo. And already we can see, well, the control and the placebo, people's cholesterol stays pretty much the same. And then once you get a little bit of time on the drug, took about a month, you actually get effects for the treatments A and B. But remember, we have people measured multiple times. This isn't cross-sectional. These are the same people at all these different time points. They're only in one line, but they're the same people. So effectively, patient is our group here. And what we really want to know is a couple things. On average, does each patient start at the same place? On average, does each person have the same type of trajectory? Right? Because certainly in different groups, their trajectories are different, but are all the A's looking the same? Are all the B's looking the same? And the controls and placebos. Now, we get a nice visual of it in JMP. It's very easy to do that. This model is actually traditionally a very hard one to fit. Mixed models have historically been very difficult. Let's fit this in JMP, and I'll show you why it's not that hard, and it's totally something you can add to your research portfolio. So let me go to Analyze again. Let me go to Fit Model. Now, we're going to do a couple things here. I'm going to put Y in first, and I'll change the personality, remember, to Mixed Model. Now, we have a fixed structure, a random structure, and we're going to actually use the repeated structure this time. We're going to look into that one. But let's first define our fixed effects. That is, what are the actual things we're doing with these individuals? And the fixed effects here is really the treatment and the time, right? So our treatment are really whether they're on A, B, placebo, or control. And then time is a factor too. As time progresses, do we think things are changing? So let's take these, and I'm going to put them in as a full factorial. What this is treatment, time, and the interaction between treatment and time. Now, our random effects and repeated structure, again, define how we want to consider the correlations within a person. Now, there's certain things we can do here, and one that I want to show you that's really powerful is called the Unstructured Covariance Structure. What this means is that we can allow JMP without using really any a priori knowledge. We can just tell JMP that every covariance, every sort of condition has a different relationship to every other condition. So we're not making any predictions that the variances are the same or the covariance structure is compound symmetric or anything like that. These are mixed model things that hopefully some of you have heard before. Now, to do an unstructured, we just have to specify for JMP who our subjects are. That will be the patient. And we have to specify what's repeated. And in this case, time. Time gets repeated. All right, so we can click Keep Dialog Open. I'm just going to click Run. actual by predicted, I'm going to minimize here, and let's actually step through this output. Now, normally I hide the repeated effects covariance parameter estimates. It's a pretty scary sounding table, and it's got a lot of stuff in here. But what I was saying before, by selecting unstructured, we're basically telling JMP that in the correlations between time points, so for instance, the correlation between April measurements and April PM measurements, so April AM, April PM, so that covariance or that correlation, we're saying has no relation to any other correlations in the data. So the correlation between May AM and May PM, right, that could actually be very similar to April AM and April PM, but we're not allowing JMP to even look for that. We're just saying they're all different. Now that is statistically expensive. Each one of these estimates cost us in degrees of freedom. And so when we eventually go down to our fixed effect tests, in this case, they're all highly significant, not really a problem, but we're burning degrees of freedom. Our denominator degrees of freedom is how much available information we have to measure error. And by wasting them, essentially, on a lot of extra terms, not necessarily wasting, potentially wasting them on a lot of terms, we certainly burn a lot of degrees of freedom. Now, the reason I like to show this example is because there's something very interesting about these data. Since we're measuring cholesterol for each individual, and we're measuring in terms of time, we can utilize something about our knowledge, really, of the phenomena to be a lot slicker in how we're estimating this model. Basically, if we look at any sort of distance between measurements, the measurements for a person's cholesterol that are right next to each other, those will be highly correlated. So if I measure your cholesterol now and in 10 minutes, across all individuals, those two measurements will be very correlated. If I measure cholesterol now and again in 2 months and look across all individuals, those measurements won't be very correlated. We know this to be true. Things that are coherent in space or close in space tend to have higher correlations. Just like the spatial argument, things that are close in space tend to be correlated. So let's take advantage of that. We can do something called an autoregressive structure. Instead of saying that all those covariances, all those time points are completely unstructurally correlated with each other, they can have whatever correlation. Let's say that adjacent levels that are close together, can be more correlated, and levels far apart can be less correlated. Let's find one correlation and scale it by how far apart people are. Now, to do an AR1, we have to use something like days. We need to use something continuous, because again, what this model will do is come up with one single correlation for how correlated observations are, and it's going to scale it by distance. So if you're 30 days apart in measurements, that correlation will be lower than if you're 1 day apart in measurement. And this will be very cheap statistically. If I run this model, notice that big scary table of covariance and variance components, right? This big table of all these different things. Well, we only have one now. We have an AR1, which is quite high correlation. But what we're saying is that correlation will scale by how far apart measurements are. And the benefit, as I said before, is that our degrees of freedom, we don't have to burn as many. Notice here we had 16 degrees of freedom, pieces of information to estimate error for treatment. Now we had 22.8. So don't worry about their fractional. That's a totally legitimate thing that degrees of freedom can have. But notice that the insight here is we have more of them on the right. And again, that's because we get to utilize a special covariance structure. And so mixed models in JMP have several of these residual structures, AR1s, unstructured. I typically like to try an unstructured and an AR1 if I have something continuous, like days. But these are certainly flexible models that allow you to measure and look into things in a way that otherwise you really couldn't do. So again, think about anytime you've measured individuals or units multiple times. That's really the domain of a mixed model. All right, so that's mixed models, a really powerful tool. So now I want to get into a slightly different idea. So mixed models, I always like to think of in very principled research. So I often have used them in these projects where I'm very carefully experimentally manipulating things. I don't do them with extant data typically. However, data mining is a different scenario. Data mining is really often thought of as like a business process, a way of mining, literally searching for patterns in your data. And so this goes by many other names. It could be machine learning, unsupervised and supervised learning. These are all different ways of talking about taking what is really data you don't know about yet or don't have a good intuition about what's happening, and you want to search. And there's a couple of special data mining platforms in JMP Pro I want to tell you about. And so the first is going to be neural networks. So JMP Regular has single-layer neural networks. We're going to be able to do multi-layer or two-layer in JMP Pro. Also special types of decision trees or regression trees. So Bootstrap Forest, which is like a random forest, and boosted tree, so gradient boosting to our tree models. And so to motivate these guys, let me pull open a bigger data set. So with data mining, it really is often better to have large data sets. And this goes back to when I was talking about validation even. It's nice to have lots of data. So here's a big data set. We have 245,000 rows here, and we have 43 columns. Now what this is, credit card churning is when you sign up for a credit card to get the perks, and then you drop the card. And so I'm staring at a Southwest credit card offer on my desk right now where they're offering to give me 50,000 miles, and you get it in your head like maybe I just want to sign up and then drop it. So credit card companies don't like that, and so they love to data mine to find ways to predict who will be a likely churner. And so we have lots of information here that could be relevant. How much they've transferred in a balance, whether they're married, what their occupation is, age of accounts, average daily interest. So there's lots of things we can do here, but this is a great data mining situation. Let's let the data suggest the structure in the world to us. And so to start this, let's actually invoke a couple data mining tools. I'm going to go to modeling, and under modeling, you'll see a number of these. So we're going to use neural, and we're going to use partition today. Let me start with the neural model. And neural models are very black boxy. And by that, I mean the functions, the activation functions are a little bit less easy to understand from the outset than, let's say, a linear model. They're not black boxy in that we don't know what they're doing. It's just that they typically are harder to explain. So don't be scared of neural models, but also don't feel like they're going to work in the same way as like a traditional linear regression would. You're not going to get p-values from this. All right, so let's actually see how we'll set this up. I'll do churn flag as my y. Neural can accept categorical responses or continuous responses equally well. Our factors are really going to be all of these. So I'll go all the way down to, I'll just go down to gender here. Now, validation, I actually already have a validation column in my data set. So I can just click that one right in here. But remember the trick. If you don't have a column in the data set selected, you can click validation and it'll ask you if you want to create one. That's a neat little JMP Pro feature. I'll tell you one final way to create a validation column. If you go under the columns menu and go to modeling utilities, you can make a validation column here. And I only show this one because when you're really working with research data, it's very likely you're going to have to stratify your validation over certain factors. So you want to balance across certain things, especially with small data sets. If we have 245,000, we can assume that randomness will take care of that. But if it's under 1,000 and you have a lot of factors, I would personally stratify my random validation column. So again, that's under the columns menu. But for us, let's just use the validation column that came with the data set. Okay, so I've entered all of these in. Let me click OK. Now the way JMP starts is we get a model launch here. And without getting too in the weeds for how neural networks work, there's essentially link functions or activation functions that allow you to create combinations of your variables. So all these variables will feed into the network, and each of these layers, so we're going to have 2 of them, can have functions that operate on the data. It really is the same as regression. You just have linear combinations of these at the end. It's just that we allow these functions to be a little bit different. So tanh are sigmoidal, and the other 2 are pretty linear or normal. So let me build a neural model, then I think it'll make a little more sense what it's doing. Let me build a typical one, so a 3-2, and I'll actually leave everything as the default. I'll just click go. Now, what JMP's going to do is, it's doing a little model fit here. I'll scroll down and show you what the model looked like. Here's a diagram of it. And so we always like to show these to people. They look so advanced, right? You can even drag things around. The point is, what this model is doing is every one of our factors is in the first layer, the values go into this activation function, the sigmoidal, and then from this activation, once they've all integrated, they can project to the second layer. And then at the very end, all these values get added together and we come up with a decision. Did they churn or not? And what's nice about neural models is without much work, we're able to get out our training, validation, and test sets. And I want to orient you to really a couple places in this output. Look at the confusion matrix for each of these, because this is really how well did our model do. So for those people who didn't churn, 59 or 5691 were predicted not to churn. And we had some false alarms. So among people who didn't, our model sometimes said yes. But among the people who really did churn, our model predicted some of them wouldn't. and actually got some of them right. So we actually get a misclassification rate here of 15.8%. So not terrible, maybe, not great either. But this is just one model, and this is just one attempt with a neural. So we can go right back up to model, and let's try just a simple one. Let's do a single layer. So a 3 and a 0. And so notice that you can try several of these models if you like, and get an idea of which one's going to do the best for predicting or classifying, in this case, our outcome variable. And so in this second case, how did we do? About the same, so 0.15. Now you can do lots of things with these models, and I want to show you one that I love to do, and that's saving the formulas. Now I actually have a couple formulas saved to my data set already, so I'm going to go ahead and delete those before I end up saving the new ones. And so I'll just go to columns, delete. Now, going back to my model here, so the red triangles, remember, always have more options. Let's save the formulas. And what this is going to do is it will write the formula for this neural model to my data set. And notice that's what it is here. And so there's this most likely churn flag at the end. And so there's a lot of rows in this data set, so it's chugging along here. But effectively what it's doing is it's calculating all these hidden layers for every single row, and it's going to come up at the end with a most likely churned flag. So it's going to tell me. So let's keep that model, because what we're going to do is we're going to try some of these other ones, and we're going to compare them at the end. And so let's try a different model. I'll go back to Analyze, go back to Modeling. Let's try a different class of models. So partition models, these are recursive partition or classification models that work by building trees. And the first thing I'm going to do is let's put our churn flag in as my y. Let's put all our factors in as our x's. Let's put our validation in as our validation. So everything looks the same as far as our setup. But now we have to look under methods. And there's a couple of these I want to orient you to. So decision tree is where we're going to start. A decision tree is a pretty simple-minded idea. We have a lot of factors, and well, actually I'll click OK and let's look at it graphically. So we have a lot of factors. If there was just one that I could use as this bank to predict whether somebody will churn, what would it be? What's the best possible one? And so if I click split, JMP will actually go through all the data and it'll figure this out. The best possible thing to split on is whether the age of the account is greater than 0 months or not missing. And if it's less than 0, then missing. So let's actually look at what this means. I'm going to go under my display option here and show the split probabilities. What this is going to show me is under here, we get a little rate and a probability. So let's look at what this model just said. If your age of account is greater than 0, well, you have a 14% chance of churning, 85% chance of not. If it's less than or missing, well, nones or zeros, right? You can't churn if you don't have an account. So that's a pretty straightforward one. Let's try another one. Let me hit split again. And it says, okay, well, if your account is greater than 0, but it's less than 12, well, you're about a 50-50 chance, it looks like. But if you're greater than 12 months with this account, you're not going to churn. You're not going to drop the card. So notice what this decision tree is doing. It's building out a little decision tree, a tree that we can follow that will maximize the difference in the rates. And we can just hit go because we have a validation column. The go button isn't there in regular JMP because JMP Pro has validation built in to let it fit this model and then stop making the tree when the validation set starts to not be more predictable. Basically, you can always predict your training data better just by adding more splits. But at a certain point, you're splitting on noise. And the cool thing about validation is that noise that's in your training set, if it's a random split, you won't have the same random noise in your validation set. It's like an out-of-sample validation. So by testing your model against your test data or your validation data, you protect yourself from overfitting. All right, so this looks scary, but here's what I'm going to do. I'm going to save my columns just like before. I'm going to save a prediction formula. So let's do that. I'll keep that model around. Let's do another version of a decision tree. And so I'm going to go back to modeling, back to partition. And this is a special type of decision tree that's not in JMP. So I'm hit recall. And the method I'm going to change to is called a Bootstrap Forest. So this is an implementation of random forests. Now, this is a really neat technique for when you have lots and lots and lots of different predictor columns. So a situation where you may have hundreds, if not thousands. And you want to make sure that you can find the active ones within that set of many predictors. Now, the way Bootstrap Forest works, the genius of it, is that instead of building a tree all at once, it's going to build lots and lots and lots of little trees that it's going to average. Now, there's a lot of things you can specify here. Our mathematicians and our statisticians work very hard to come up with the best starting points. So I often don't even touch this. I can't beat what they came up with. And so this Bootstrap Forest, when I run this, it's now going to build up to 100 trees that are little, each of which only have 10 splits. And by doing this, you build trees that don't have all the predictors in there. You're taking a sample, really, of your predictor space. And the benefit is that sometimes you will have predictors that'll trump other ones. And so you'll never get to see that there are actually some really good columns in your dataset that could be predictive if only you didn't have this other thing that was masking it. And so a Bootstrap Forest gets around that issue by taking a subsample of not just rows, but also columns. And so it builds the model in the same way, and we get the same classification. So this one had a 0.05 misclassification rate. We're doing even better now. So let me save this model. I'm going to go to Save Columns. Let's save the prediction formula. And I'll show you why I'm going to do that in a second. And let me do one final model. This one's also only a JMP Pro. And so let's go back to modeling, go back to partition. I'm going to recall. Instead of Bootstrap Forest, I'm going to do the boosted tree. So boosting is gradient boosting. What it is essentially is fitting small trees, and then the residuals from that model are the data for the next tree. And so they're fit into layers with a particular learning rate. And again, these initial settings have been picked purposefully, so I often leave them as well. So boosted trees, this may take a little bit longer, so it's fitting lots of these. And I should mention, what is taking my computer 30 seconds 5 years ago would take a server like a week. So these algorithms, our mathematicians have done incredible things. They've just gotten so fast. And so these type of data mining procedures, even with just a laptop, are very in the realm of things that we can all do. And this is not a small data set either. So here we go. And so we got our misclassification rate, 0.05 as well. So gradient boosting, very similar. Okay, so I'm going to save these. And I want to tell you why I'm saving all these prediction formulas. The reason why is we just built a number of models. And it's often important for us to compare the predictability of them, or what they're really asserting about the world. And so what we can do with JMP Pro is under this Analyze menu, under Modeling, there's this Model Comparison Platform, which is built to do exactly the thing I was just saying. I need to compare all those models. And we can actually just leave this totally blank. JMP knows to pick out the formula columns. And what it's done is created us a measure here. It's actually showing us for all those different models what the predictability is. Now, the way JMP is doing this is it's actually looking at really how well the model predictions match up with the real values. Now, remember, we had validation. So let me show you something really neat here. If I go back to model comparison, and instead of leaving it all blank, I'm going to take that validation column, and I'm going to use it as a bivariable. Bivariables in JMP replicate an analysis across the levels of the variable selected. And so in this case, I'll get separate outputs for my validation 0, 1, and 2. That is for my training, my validation, and my test set. Because really, the one I want to look at is how my model does with data it never got access to seeing. So how did these models do with data it never was able to fit with? And in this case, we can see we did really well with our boosted tree. That got our misclassification rate to the lowest. And we can do one more here. Under the red triangles, remember, there's lots of additional options. We can get ROC curves for all of these, a great way of looking at predictability. We can get lift curves. One that I love, though, this is the profiler. The way to make sense of the model, like we did before, was, well, let's look at each of the predictors and how those predictors relate to the responses. And so notice that if we look at age of accounts and move this around, you can actually see how it'll affect the response. Now, what's kind of neat is you also get an insight into how these models think about data, right? When you're in the boosted tree or any kind of a tree model, you get this kind of jaggedy shape. But typically, when you're in linear models, you would never see anything like that. All right, so again, that's the prediction profiler that's under your model comparison. All right, so before we leave the data mining section, I did want to mention a special kind of data mining model called an Uplift model that it has certain uses, but I want to show you one that I think is really neat. And let me open up just the typical canonical data set for this. So it's called hair care product. And this is a very simple idea. So hypothetical data where we have a big set of people in our company database, and we're sending them promotions. We send half of them a promotion for a product. And we want to know, does that promotion make people purchase? right? And we hope it does. But we can do one better than just seeing, did the promotion work? We want to know, for whom did the promotion work? For whom was the promotion maximally effective? Because if we know who those people are, then we can send the promotion to just them. And so uplift modeling is a way to do that. So again, it's not going to be under partition, but it's actually under consumer research. I'll tell you why a little bit more later. Now it's going to look a lot like a decision tree. And in fact, it really is. It's a type of partition analysis that's trying to maximize the difference between the people who were treated one way and the people who weren't. So let's put promotion in as our treatment. Purchasing is our response. And these are our predictors: gender, age, hair color, residence, all of that. And I'm also going to put my validation in. Always use validation if you can. I'm going to click OK. We're going to get this kind of an impenetrable plot until you know what it's doing. So I'm just dragging up the axis because the purchasing rate was really low on average. On average, people purchased at a rate. Let's actually double click the axis and let me add in some minor ticks here. And let me put it at 0.05. There we go. So the average purchasing rate is this middle line here. So the one right there. And this little step is showing among the people who didn't get the promotion, which is these people, what's the rate of buying? And among the people who did get the promotion, what's the rate of buying? So it's a little bit higher if you got the promotion. But remember, the question is, we want to know for which subsample of people is this step going to be maximal. So we can click go because we have a validation column, but I'm going to click split just to see it first. And notice what it split on first. It said gender. If you're male, the rates are basically the same if you got the promotion or not. You're not buying or you're not being affected by the promotion. But if you're female, you get a huge step. So from 7% up to 20, or sorry, yes, 0.07, less than a percent up to 2.1. And so that's incredible. We were just able to basically make a business decision. We should never send our promotions to men. But we can do better. We can keep going or just hit go, and it'll build out this tree eventually to the point where it says, okay, the people we send it to should be females who have this particular hair color, black, brown, or red, or if they're blonde, we got to make sure that they're less than 42 years old. All right, so that's a really neat model, and that's great for, sure, if you're marketing. But I came across just this morning a really neat article of where people were using it not for basically just marketing. Let me actually pull up this PDF because it's too cool not to show. But not just for marketing, but for medicine. And so uplift modeling in clinical trials. And so this was a really neat paper just a couple of years ago, and they were able to demonstrate that even these clinical treatments that don't work for most people, by using uplift modeling, they can find the subsets for whom it really works. And so uplift modeling, even though it's a commercial thing, this is absolutely something that can change lives. And so if any of you end up using uplift model for clinical, please email me. I would love to see some case studies of this being used. But I was just really happy to see that that's something that people have thought of. And so again, it's a type of model that's going to let you find the place where there's maximal difference. And it doesn't have to be a yes or no decision. It could be anything. It could be numeric if you want. So we can find, where the manipulation maximally separates people's cholesterol. For whom does that drug most work? And that's good data to know. All right, so that's uplift modeling. Now, before I close out of that one, actually, let me just poke through a couple of these. I know we're getting very close to the end, so I want to make sure you at least know what these other sections do. Model comparison, I just told you about. In the context of our data mining, we saved a bunch of formulas. And again, that's just under Analyze, Modeling, Model Comparison, and a great way to look at the different predictions of your different models. Now, the last of these two are really actually big classes of new analyses. So partial least squares and generalized regression. And I want to talk about them together because in a sense they can be used for similar situations. So partial least squares, the principal cases are when you have a large number of predictors, and you may not even have as many rows as you have predictors. And so I'll pull up the canonical example for this one. So if we're looking at spectrometric calibration, so this is data from the Baltic Sea, and what they're trying to do is they're trying to calibrate their spectroscopy. So they have these three different substances. One of them, LS, I think that's an industrial pollutant. This is a natural forest product, and this is a whitener in detergents. Right, so these are potentially contaminants that are in the Baltic Sea, and we have measurements, 16 of them, 16 different samples that have the actual amount. So we not through spectroscopy, but through another process, figured out exactly how much of each of these was in it. And what we also have is the spectral intensities, and we have 27 of them. So notice we have 16 rows and we have 27 predictors and 3 y variables. That's not something regular linear models can handle. Regular least squares won't work. That'll be super saturated. Multicollinearity is another issue. So we have, in this case, spectra that are all going to be very highly correlated with each other. So if I just show you this, let's do it under multivariate. Let's look at these intensities. So if we look at these correlations, they're all around 0.9, 0.8, 0.9. I mean, there's so much collinearity here, correlations in the predictor space, that a typical linear model will get unstable. And so partial least squares is one way of handling this. And it's a different way of handling it than what generalized regression will do. Generalized regression is a special way of handling lots of things, so screening predictors, handling multicollinearity, but it does it in more of a model selection way. What partial least squares will do is, in essence, it'll principal component both sides of the equation. So we're going to extract latent structures on the right-hand side of the equation in the predictor space and on the left-hand side. So let's look at how this works. So in JMP Pro, there is a personality here under fit model for partial least squares. Now in regular JMP, you can do some of this, not through fit model, but through the partial least squares platform. But in JMP Pro, you get a huge number of more things, and especially these. So centering, scaling, standardizing, it'll all handle for you automatically. And so I know we're running low on time, so let me just show you what this looks like. I'll take the 3 different pollutants. I'll put all the intensities in as model effects. Again, these are equidistant spectra. We just didn't label them with their wavelengths. I'll hit run. Now, JMP starts off with a model launch. You have some different options here. NiPals is nonlinear iterative partial least squares. Definitely say it as ni, not ni, otherwise you get into trouble pronouncing that one. SimPals is a different way of doing it. Validation method is ways we can do this for reasons we can talk about offline. If you're interested, I'm going to do leave one out, the best validation when you have a very small data set. And I'm just going to click go. Now we're going to get a lot of stuff, but let me just point you to one place right here. So the amount of variation, cumulative, that's explained in X, we explained with this model almost everything in the predictor space and almost everything in Y. That is, on the basis of this model, we can classify or predict those pollutants based on spectra. And we can do it really, 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 really well. And there's a lot of detail here on how it works, but let me just show you the way that you would actually use this model. Once you fit your NiPals model here, I would actually just go and I would do save columns and save the prediction formula. And now, when I go and get new data from the Baltic Sea, I can just put them into this table with the spectra, and JMP's going to calculate for me that prediction. And so I have, in essence here, just calibrated my spectroscopy. So without any work, really, JMP Pro was able to do it. Now, generalized regression would come to this in a different way. So let me switch over to that platform very quickly. So fit model. And notice the generalized regression right next to, here's partially squared, right next to mixed models is generalized regression, which I'll tell you is a very general, given its name, type of regression. It can do Cauchy regression, normal, certainly all the different link functions, these zero inflated models too. I'm just going to leave it on normal. Let's put in just one of these, let's say LS. And if we put our intensities in as our Y, I'll hit run. Now, generalized regression really is several different types of regression. So once we invoke the normal, we can do a lasso, a ridge, or a marriage of those two, elastic net. Now, again, without getting into the weeds, lasso will help with variable selection. The way it does the penalty on the model is in such a way that it does a good job at picking variables. Ridge regression does a great job at collinear variables, so it will not have a real problem with multicollinearity. And elastic net kind of marries these two techniques. So I'm just going to specify that, and for this one, let's just do leave one out again. So same. I'm going to hit run. So what's interesting about generalized regression is it will be an interactive modeling platform that certainly merits an entire webinar on its own, and there is one out there you can get. But what it does is, in essence, allows you to drag through the path of your model, and it's a penalized method. So what it will do is, as it allows you a bigger and bigger budget for parameters, the most important ones will enter into the model. And what you'll see here is eventually get to a point in the green where the best model is found. And so what this did is it ignored pretty much everything else and just used one spectra. And by doing that, it actually did pretty well. If we look at the sort of the model summary and some of the details here, even the effect tests, it's doing an okay job with just one spectra. And so generalized regression is a whole different approach to this. So partial least squares will use everything in a sort of a collapsing way, principal components way. Generalized regression will help you search a space and find the important predictors. All right, so I think we actually just ended right on time there. And so to learn more, certainly visit our website, jump.com. I want to point you to a very special place, though, the Jump academic community, where we on the academic team work really hard to aggregate the resources that we think are really most useful. So if you go there, let me drag this off my other screen. What you'll find is top resources, so data sources, our webinar recordings. I'll definitely put this one up there later today. We have case studies. We have one-page guides. These are videos and PDFs on how to do things in Jump. And so I really encourage you to look at our resources. And certainly look at jump.com, our on-demand webinars, for a lot more of the pro features. I would recommend the Mastering Jump webinar series. All right, so that's the end of our webinar for today. My email is right here, so if you have any questions about anything you saw, or you want to know where to learn more or where to see more, please reach out to me, and I would love to get you started. And again, I do want to say, if anyone ever uses Uplift modeling for clinical trials, please get in touch with me. I think it's just what an amazing thing to be able to find the subset of your patients who most respond to your treatment. I just think it's going to open up a lot of doors once it catches on. So thank you all very much for joining us. We'll send an email out with the links to the video once it's available, and certainly reach out to me if you ever have any questions. So thank you all so much for joining us today.